Hi there, and welcome to the third lesson in our series, Introduction to Electronics. In our previous lessons, we investigated what happens when a potential difference is applied across the ends of different materials, including conductors and insulators. We used energy band theory to show why conductors allow charge to flow through them and why insulators do not allow charge to flow, except under extreme conditions of high potential difference and high temperature. Now, in today's lesson, we will examine what effect applying a potential difference has on materials made from a group of elements that are found on the periodic table between the metals and the non-metals. Of course, we're talking about the semiconductors or metalloids. As the name suggests, these substances have some properties of metals and may conduct electricity under certain conditions. Let's find out exactly what these conditions are and then use energy band theory to explain these observations. We'll also see how people have adapted semiconductors in a process called doping to make useful electronic components. By the end of today's lesson, you should be able to use energy band theory to explain the effect electric current has on semiconductors. Describe how semiconductors are adapted by doping, and evaluate and compare the effect of P and N type doping. Silicon is probably the most famous semiconductor. It is found in most electronic components, such as transistors and tiny integrated circuits we commonly call chips. Let's begin today's lesson by investigating what happens when a sample of silicon is connected into a circuit and a potential difference is applied to its ends. Off to the lab.
Chips, anybody? Okay, seriously, silicon chips can't be eaten. But then make sure that your digital appliances, like TVs, cell phones, and computers work. Have a look at the apparatus I've set up. I have a power supply, an ammeter, a voltmeter, a rheostat, some connecting leads, and a sample of silicon.
Hey, this looks just like the apparatus we used for the conductors when we confirmed Ohm's law. Even the silicon wire looks a bit like metal.
That's right. We're going to use the same sort of investigation, except I want you to heat up the silicon wire and you to keep it cool in dry ice. Any questions before we start?
Please can you just remind us of the readings we must take?
Sure. Remember, you'll control your current using the rheostat, and you'll need to record the current passing through the silicon wire and the potential difference across its ends. Ready to start? Remember to take your readings quickly to keep your temperature low. Klanga, you should heat the silicone rod continuously with the spirit burner while you take the readings. Take at least 5 readings and record them in the table. How are things going?
I don't seem to be getting any results. I have checked that my meters are connected correctly, but whenever I test the silicon, I get very small current values, even though I've changed my rheostat.
Try increasing the potential difference on the power supply.
Okay. Look, even though the power supply is at a maximum, the silicon does not allow high values of current to pass through it. Are you sure silicon isn't an insulator?
Well, that's an interesting conclusion you've made. But before we see if it's correct, let's see if Klanga's got any results. Were you able to get any results while heating the silicone?
Yes. As the current increases, the potential difference increases too. This silicon seems to be behaving like a conductor. Should we draw a graph to be sure?
Well, you could, but you could also check if the resistance is constant by dividing the potential difference by the current and seeing if the value is similar for each of your readings. That's why silicone is a semiconductor. Under low temperatures, it acts as an insulator. Under high temperatures it acts as a conductor. Can you use the energy band theory to explain these results? Let's go to the studio and see how it works.
Welcome back. Let's look at some graphics to explore how energy band theory explains the results we saw in the lab. Silicon has 4 valence electrons that bond covalently to form a giant molecule. The electrons are tightly held in the valence band. As with insulators, the conduction energy band does not overlap with the valence band in silicon. But in the silicon, which is a semiconductor, the gap between the valence band and the conduction band is smaller than in an insulator. At low temperatures, there is not enough energy for the electrons in the valence band to move into the conduction band, and so silicon does not conduct electricity at low temperature. But when the silicon was heated by the spirit burner, the electrons in the valence band gained enough energy to move into the conduction band. However, these excited electrons left behind a region that is now positively charged in the valence band. These positive regions are called holes. Now, when a potential difference is applied to the ends of the semiconductor, the electrons in the conduction band move towards the positive terminal of the battery. At the same time, something interesting happens in the valence band, where there are holes present. Let's focus on what happens around one hole when a potential difference is applied to the ends of the semiconductor. An electron in the valence band is attracted to the hole and fills it. The hole is no longer positive, but neutral. However, a new hole has formed where the electron came from. Notice that the direction the electron moved in was towards the positive terminal of the battery, but the hole, or positive charge, appears to move in the opposite direction, towards the negative terminal. The apparent movement of holes in the valence band, together with the movement of excited electrons in the conduction band, is the reason you detected a current passing through the silicon when it was heated. But when the silicon was kept cold, the electrons were not excited and remained in the valence band. That's why silicon is called a semiconductor. A semiconductor is a material that acts as both an insulator and a conductor under different conditions. Now, when scientists first began to experiment with semiconductors like silicon and germanium, they did not always have pure samples of the element. The impurities present in the sample meant that they did not get consistent results. The presence of certain impurities allowed these semiconductors to act more like conductors. This led scientists to experiment with mixing specific impurities into samples of silicon or germanium. This process is called doping. Let's have a look at a model of a silicon crystal to see how this doping process works. Silicon has 4 valence electrons and forms 4 strong covalent bonds in a giant molecule. Here we have shown the bonds acting at 90 degrees to each other in a 2D model. The electrons in this crystal are all tightly held in the valence band. Now, there are 2 types of impurities that can be introduced into a silicon crystal. If you look on the periodic table, you can see that to the left of silicon is boron and to its right is phosphorus. Both these atoms are of similar size to the silicon atom and can take the place of a silicon atom in the lattice. Now, let's see what happens when we introduce a single atom of phosphorus in the place of a silicon atom. Notice that the phosphorus atom has 5 valence electrons, so there is now an extra electron in the silicon crystal. This loosely held electron moves into the conduction band when a potential difference is applied to the ends of the material. We call this type of doping N-type doping because the impurity has added an extra electron which carries a negative charge. Can you predict what would happen if boron was introduced as the impurity into the silicon crystal? Well, boron has only 3 electrons, so if a boron atom took the place of a silicon atom, there would be an extra positive charge or hole in the silicon lattice. This means that the crystal would be positively charged overall, and so this is called p-type doping. You have to keep in mind that even though the n-type and the p-type silicon behave as conductors, they are not the same. Let's see how charges move through each of these materials by looking at a microscopic model. When a battery is connected to the ends of an n-type semiconductor, the extra electrons move into the energy gap just below the conduction band and move toward the positive terminal of the battery. So, in an n-type semiconductor, the electrons are called the majority charge carrier and move towards the positive terminal of the battery. Now, what do you think happens in the p-doped semiconductor? Let's have a closer look at the microscopic model in this case. The holes formed by a p-doped impurity have an energy just above the valence band. So, when a potential difference is applied across the ends of the semiconductor, electrons in the valence band are excited and fill these holes. These electrons are pulled towards the positive terminal of the power supply, while the holes appear to move in the opposite direction, towards the negative terminal. In a p-type semiconductor, the holes are the majority charge carrier. I think you can see that although both the n-type and the p-type silicon behave as conductors, the way in which the charges move is different. In n-type material, the extra electrons are the majority charge carriers and move in an energy level just below the conduction band. The electrons move towards the positive terminal of the battery. In p-type material, the majority charge carriers are holes found just above the valence band. The holes appear to move towards the negative terminal of the battery. Now that we have looked carefully at semiconductors, I want you to complete an investigation for your task today. Sodium chloride is an ionic solid. Plan an investigation to determine under which conditions this substance is a conductor. Explain your answer by using a microscopic model of this material. In our final lesson, we will carefully explore what happens when N and p-type semiconductors are joined together, and how this type of junction is used in electronic components called diodes. See you then.
Yeah.